In this final video, we'll look at regression analysis, which is perhaps one of the most widely used analytic methods. In general, the objective of regression is to quantify the relationship between a dependent variable y, also known as a criterion variable, and one or more independent or predictor variables x. We use regression both to understand the effects of the x's and to predict or forecast the value of y for given values of the x's. It's a widely used technique employed in almost every field, from marketing, where it is used to predict sales as a function of marketing mix variables, to economics, where it is used to predict the gross national product based on macroeconomic variables such as money supply. The basic or simple regression model assumes that y equals an intercept term beta naught plus a regression coefficient beta 1 times x plus an error term epsilon that captures the impact of any other factors that affect y but are not observed. The intercept term represents the mean value of y when x equals 0. The slope or coefficient of x represents the change in the mean of y due to a 1-unit change in x. A simple regression model has just one x, and when you have more than one x, it is called multiple regression. Here's an example of how we would run a regression analysis using SPSS. In this dataset, the dependent variable is weekly store sales, and the independent variables are ad, a categorical variable that represents whether an ad is displayed in the store that week, and price, representing the price of the product that week. We will use regression to determine if ad and price had any impact on weekly sales. Click on Analyze, Regression, Linear. Define the dependent variable, sales, and independent variables, ad and price. Click Statistics and check Estimates and Model Fit. Click Continue and OK. Here's what the output looks like. The model summary shows the R-square or percent of variance explained by the independent variables in the model. Here we see an R-square of 0.48, meaning that 48% of the variance in weekly sales is explained by the model. The ANOVA table tests the hypothesis that the explained variance is significantly greater than 0. The p-value for this test is less than 0.001, meaning the R-square is significantly greater than 0. This confirms that the model does explain variance in sales. The most important table is the last one, labeled coefficients. This shows the results of testing whether the coefficients of the independent variables are significantly different from 0. As you can see from the last column, the p-value for the coefficient of ad is less than 0.001, while the p-value for the coefficient of price is 0.943. As usual, we compare these p-values with our chosen alpha, and if the p-value is less than alpha, we reject the hypothesis that the coefficient is 0. So, ad is highly significant in its effect on sales, but price is not. Since price is not significant, we can go a step further and rerun the model without price as an independent variable. In this new model, you can see that the R-square has not changed at 48%, and it is still significantly greater than 0. The coefficient for ad is still significant, and it still has the same effect on sales as earlier. In other words, removing price did not change anything other than the value of the intercept, that is the constant term. Based on our results, here is the final regression model with only ad as the independent variable. Sales equals 1195.19 plus the coefficient for ad, which is 1266.01, times the value of ad. What are the predicted sales when there is no ad? When ad equals 0, that is, there's no ad, sales equals 1195.19 since the second term is multiplied by 0. Now, what are the predicted sales when there is an ad? When ad equals 1, that is, there is an ad, sales equals 1195.19 plus 1266 since the second term is multiplied by 1. So the sales equals 2461.2. In the previous example, we had an independent variable that took the values 0 or 1. Regression assumes that your data are quantitative in nature, but there is one exception. You can include a variable that has values of only 0 or 1. This is called a dummy variable. In the previous example, the variable ad was assigned values of 1 and 0 to indicate the presence or absence of an ad. Assigning a value to a variable is called coding the variable. so a dummy variable is always coded as 1 or 0. What happens when you need to include a categorical variable that has more than two values? You would need to represent them via a series of dummy variables, each coded 1 or 0. In general, to represent n groups, you need n-1 dummy variables. For example, let's say you want to include consumer type as an independent variable in the model, and there are 4 types of consumers in your sample: brand loyals, variety seekers, impulse buyers, and rational buyers, coded 1 through 4. To include this variable, you would have to create 3 dummy variables, D1, D2, and D3, to represent the 4 types. As you can see in the table, when the consumer is brand loyal, D1 is coded a 1 and everything else is coded a 0. For variety seekers, D2 is coded a 1 and everything else is coded 0, and so on. You could then run a regression with D1, D2, and D3 as the independent variables. Once you get the output, and assuming the coefficients are significant, you could predict the dependent variable by plugging in the values for each of the dummy variables for a given consumer type. For brand loyals, the prediction for Y would be the intercept plus the coefficient for D1, since all the other terms would be 0. For variety seekers, the prediction for Y would be the intercept plus the coefficient for D2. For impulse buyers, the prediction for Y would be the intercept plus the coefficient for D3. And for rational buyers, the prediction for Y would be just the intercept, since all the dummy variables would equal 0. In closing, we should be aware of the assumptions underlying regression, because regression may not be appropriate if the assumptions are violated. First, it assumes that the relationship between variables is linear. If this is incorrect, then regression can give you very misleading results. Second, it assumes that errors, that is, the effects of unobserved factors on Y, are normally distributed with 0 mean. Third, it assumes that the errors are uncorrelated with each other, that is, errors for each data point are independent of each other. And finally, it assumes that the independent variables, the x's, are independent of each other, that is, uncorrelated. Researchers sometimes feel the need to test whether these assumptions are being violated, and if there is evidence that they are, there are ways to work around these problems. However, because we are not looking at the technical aspects of regression in this class, we will not go into these methods. You need to take an advanced course in statistics or econometrics if you want to learn more.